I do so many problems. It's like a straight attack. This is 2551. Put marbles in a bag. Bag. You have K bags. You're given a zero indexed integer array weights, where weights of I is the weight of the ith marble. Okay, so you have this array weights. It has length n. There's n marbles. Each element at each index is the weight of the marble at that corresponding index. You're also given the integer k. Divide the marbles into k bags according to the following rules. No bag is empty. All right. If the ith marble and the jth marble are in the bag, then all marbles with an index between ith and jth indices should also be in that same bag. If a bag consists of all the marbles with an index from I to j inclusively, then the weight of the bag is the weights of the ith marble and the weights of the jth marble. Okay. The score after distributing the marbles is the sum of the cost of all the k bags. We want to return the difference between the maximum and the minimum scores among marble distributions. All right. So, where do we get started here? So, I guess the first thing I noticed when I approached this problem was, well, you know, no bag is empty. The ith and jth marble are in the bag. Well, like, you know, since no bag is empty, and if we put the ith marble in a bag and the jth marble in the bag and all the marbles between them are in the same bag, you know, if you have, for example, 1351, right? So we have weights equaling 1, a 3, a 5, and a 1. And we have k equals 2. For this example, you know, we have two bags. So there's these two bags. You know, we'll call this bag A, baguette, and bag B. Now, these bags can't be empty. And if you decide to put two marbles at different areas in one bag, all the marbles in between them also have to be in that bag, right? So if I said that bag A was green, right? So this is a green bag, I guess. And bag B was red. So this is a red bag. If I was to put marble with the value 1 and marble 5 in bag A, I'd have to also put marble 3 in there, right? Because the rule is if I put the ith marble in the bag and the jth marble in the bag, I have to put everything in between in the same bag. And since no bag can be empty, well, then that would mean that I'd have to put 1 in this bag, right? Likewise, if I took this and I decided that I wanted to put, you know, 3 inside of bag B, well, then it would have to look like this. So I guess another way of thinking about this problem, given the way it's constrained, given the way the problem's stated, is that you're really just partitioning this array, right? You're partitioning the subarray into components where you decide what bag each set of those components are going to be in, right? So essentially what you're doing is you're just finding a split point where you're deciding where you're going to split these elements, right? If I put a split here, that means that everything to the left will be a partition and everything on the right will be a different partition. If k equals 3, then I can make another partition like this. And that would mean that everything on the left of this first partition is in one bag, everything between these two partitions is in another bag, and everything to the right of this last partition is in the third bag, right? Because it's just based off this constraint here. Well, these two constraints. There's no bag is empty, so there's no non-empty, there's no empty partitions, and you can't like split up the marbles. They have to go together, right? Like if you put the ith marble in the bag and the jth marble in the bag, everything in between it also has to go in the bag. So because of that, it really just boils down to fundamentally looking at this problem as taking an array and breaking it into partitions. So we don't even need to think about the fact that we have marbles and that there's bags. We just need to say, okay, there's k partitions, right? We want to partition this array into k partitions, and we want to find the minimum cost, the maximum cost based off this idea here. Okay, so let's rethink of this problem, right? I guess our first observation is this problem is equivalent to k partitions of an array with an additional, or let's call it a unique weight constraint. So the weight constraint is also different. So now when we look at this problem, we can just think about it in terms of k partitions. So if we have 1, 3, 5, 1, right? What we're really trying to do is find the minimum and max partitions. And the partitions for k equals 2, so we can partition this thing in any two ways, right? So what are our partition points, I guess? Well, we can't have an empty partition because that will correspond to an empty bag. So we could take this line, right? We could put it here and partition here. So it'd have 1 is one partition and 3, 5, 1 is another one. We could partition here. We could have 1, 3 is one partition and 5, 1 is another one, which corresponds to having 1 and 3 in one bag and 5, 1 in one bag and another bag. And the idea, of course, is because since if you put the ith and the jth element in the ith and jth marble in the bag, you have to put everything in between. So it constrains the system to this partition idea. Or this, right? So those are your 3 choices for a partition. Right? So if you have, so I guess the second observation is a smaller observation, but you know, if you have k partitions, then there are k minus 1 split points. And what I mean by split points is, you know, there's k minus 1 places where you can decide to divide your subarray, right? Since k equals 2, there's one place that I can decide to split this array to make 2 partitions, right? If k was equal to, you know, if k was equal to 4, that would mean I had 3 partitions, or there would only be one such way to do it, right? But there'd be 3 ways that I'd split this thing because that would result in, you know, 1, 3, 5, and 1, right? So there's 4 partitions now. So if you have k partitions, there's k minus 1 places where you could split the array to create a partition. Now, the interesting thing about this score is that the score is only based on the first element in the partition and the last element in the partition. So when we're dealing with, let's just look at this example. So if we wanted to get the maximum score, let's start there. Well, if you took a partition here, then you would get the resulting arrays, subarrays of 1, 3, which corresponds to putting 1, 3 in one bag, and 5, 1, which corresponds to putting 5, 1 in another bag. And your scores would be 1 plus 3 and 5 plus 1. So that happens to be the sum of the subarray here, but let's do the example. Let's slightly adjust this example so that it's a little more obvious how this is supposed to work. Actually, no. So 1, 3, 5, 1, right? Because 1 and 3 would be the first and last element of the subarray 1, 3, and 5 and 1 would be the first and last element of the subarray 5, 1. So you get a total score of 10. If you had 1, and then if you want the minimal score, you would split at this point, and then you'd have 1 and 3, 5, 1. So now this one kind of gets the point better. You know, this score will give you 1 plus 1, because the first element is 1 and the last element is 1 in this partition. And this will give you 3 plus 1, because the first element of this partition is 3 and the last element of this partition is 1. And your total score would be 3 plus 1, 4, plus 2 equals 6. So the first partition gave you 10. The second partition gave you 6. So 10 minus 6 equals 4, which is the output of this problem. Okay? So what this problem really boils down to fundamentally is, you know, disregard this idea of marbles and bags. Really, it's just partitioning an array into k subarrays. And you want to find the maximum score, where the score is for each partition the sum of the first element and the last element of each partition, and the minimum partition such that the sum is, again, the first element and the last element of each partition. And then you want to subtract that from the maximum. So subtract the minimum from the maximum, find the maximum, find the minimum. Okay. So I guess the greedy approach here that I realized pretty quickly is well, the only way you only get a score, right? You only get a score at partition points. So to find the max score, you'd want to find the max partition points. My writing is so terrible. Find max. I'll try to write better. Ugh. Partition points. So you only get a score at partition points. So you find the maximum score you'd want. So to find the maximum score, you'd want to find maximum partition points. What that basically means is, like, if I had a very simple example, if I had 0, 0, okay, if I had 1, 0, 0, 0, 1, 1, 0, 0, 1, and I wanted to partition this into k equals 2. Well, that would mean that I have k minus 1 split points. So that k minus 1 partition points or split points, right? Well, I only get a score if the elements are at the end or the beginning, right? If they're the first element in the subarray or the last element in the subarray. So that means I would want to put the partition here, right? Because then I would get this one and this one and this one and this one, right? Versus if I wanted the minimum split point, well, then I would want to split it here, right? Because it would only add up this one and this one and this one and this one, right? If I put the partition point here. So you can kind of see from this that if you want to maximize your score or minimize your score, it's all about where you partition, right? Because we know we have to partition, right? If we have k equals 2, we're going to have to put one partition point. So we should put that partition point in a position where it maximizes your score. And that is really just corresponding to the element that's on the left of the partition and the element that's on the right of the partition, right? Because for any partition, right, if you partition an array, that's going to create 2 subarrays, right, at some point, regardless of how many partitions they are. As soon as you partition, both elements that are on both sides, right, the elements that are on both sides of that partition will get summed up in your score, right? Because as soon as you make a partition, this element on the left becomes an element that you're going to add because it's the last element on the left partition, right? Because you partitioned. So now there's 2 new subarrays that you're creating. So the element on the left is the last element of the partition that you create on the left. So that's going to get added to your score, right? So that's going to eventually get added to your score. And whatever's on the right of your partition, B, will be the first element of the partition to the right of the split. So that will also get added to your score. All right, so whenever you split, whatever elements you split between, those will get added to your score. So if you want the maximum score, you should just do splits where it would maximize your score. So which 2 elements together would create the maximum score. And if you wanted to minimize your score, you'd want to find the elements such that at that split point, those elements' values are minimum. And then you would just do that for k splits. Whatever the number of splits you have, you should just grab those splits accordingly. Okay. So where do we go from there? So for this problem, right, applying that idea to this problem here with one, 3, 5, and 1, right, and k equals 2. Well, if we wanted the maximum, right, well, if we would put the split here, right, because we already know that I guess one thing that's interesting, right, is that the first element and the last element of your original array will always get added up, right? They'll always get added up because they'll always be the part, this 1, no matter where you split, it'll always be the first element of some subarray. So you're always going to end up adding this one, and you'll always end up adding this one as well. So then it just becomes about where you make that k equals 2 split, right, to create 2 subarrays. So if I split here, right, if I split here, then I'm going to get an additional 1 and an additional 3. So I'd get an additional 4 if I split here. If I split here, I get an additional 8, right? Because if I split here, then 3 will be the last element of the previous partition, and 5 will be the first element of the next partition, which is what you add according to this constraint. And if I split here, I'll get 6. So obviously, using this information, the best place to split to get the maximum score would be this 5. Would be here. And that would give me a score of +8. Now for min, interesting thing again is, remember, regardless of where you split, the first element and the last element of the original array is going to end up being added up into your solution, because the first element will always be the first element of any place you partition, and the last element will always be the last element regardless of where you partition. So again, you're going to get this 1 + 1. But which one of these partition points would result in the lowest score? That would be 4. So +4. So then your total score would be 8 + 1 + 1, which is 10, minus 4 + 1 + 1, which equals 6, which equals 4. Now this will work for any number of partitions, right? Because for any number of partitions, it doesn't matter where you put previous partitions or next partitions. If there's a point where you could partition that would increase your score, you know, that's kind of the greedy argument. And there's probably a formal proof, but I think it's intuitive enough in itself that we don't need to go down that route to prove it to ourselves. So then, what's the approach here? Well, I guess the first thing is we don't even need to think about the first and last element, right? Because since we're subtracting these things from each other, and so they'll both always include the first and last element, they'll just negate each other, right? Because I'm going to have to add the first and last element for max, and I'm going to have to add the first and last element to find min. But since the score is just about the difference between them, you know, I don't need to actually know that the maximum is 10 and the minimum is 6, right? In this example, I just need to know the difference between the maximum and the minimum. So knowing, you know, adding up the first element and the last element doesn't really help. We just need to find these partition points, right? Because the solution is also 8 minus 4 to get B4. So how are we going to do this? Well, what we can do, right, is we can just create this partition. We'll call it partition score, I guess. And what is that going to be? Well, for each weight, I plus weights of I minus 1, right? Because if you partitioned at this point, that's the score you would get. For I in range length of weights. Let's make me a little bit smaller here. So let's print the partition score. Weight is not defined. Oops. Okay. So this is saying at index 1, if you split at this point. Oh, shoot. So we start at 1, right? Because there's nothing for the 0 thing to compare before it. Okay, so if you split at this point, you get a score of 4. If you split at this point, you get a score of 8. If you split at this point, you get a score of 6. Okay? Now, if you have K bags, there's K minus 1 places you can split. But you only want the K minus 1 largest split points if you're dealing with maximum, right? Because if you had, like, for this, you know, for this solution, there was 3 split points, but we only want the one largest one, right? We want the K minus 1 largest split points. So for this, you could just find the maximum of this just 1. But imagine you had K equals 100. That means you need 99 split points. right? You need to look at all 99 split points and say, okay, and I just want the I just want the 99 largest split points. Imagine you had a huge array, had 1,000,000 elements, so you had 1,000,000 minus 1 split points, and you wanted the 99 largest split points, right? Because those would be the points of which would maximize your score. In order to do that efficiently, you can't just like look for one thing, right? You need to look for the 99 largest things. So in order to do that, we're going to use a heap, right? Because with a heap, you can push things and then pop things. So what we can do is we can just say, well, let's return the sum of heap q dot n largest. So this is a library that will efficiently, using n log n time or k log k time, find the n largest thing. So if we're talking about n in terms of what's the input here, so n log n time, it'll find the n largest things within an array using a heap, right? So it'll just keep pushing and popping to find the n largest things. So we're going to want to find the k minus 1 largest things from partition score, and that will give us the k minus 1 largest points. So that'll give us the largest score that we could get, minus the sum of the n smallest things, right? Because the n smallest things correspond to the minimum score that we could get, and then the difference between them. All right, there we go. This runtime is bad, but not a problem. So what is the time and space complexity of this? Okay. So for time and space, so the problem is there's a quicksort way of doing this. I'm not going to cover. And quicksort has like, you can claim O of n. I haven't looked over it enough. You can say, not quicksort, quick select. But quick select is technically n squared, but so is quicksort. And we still call it whatever. So quick select could give you an ON algorithm, but also technically it's an ON squared. This is why time complexity, space complexity isn't exactly a bulletproof approach of looking at a system, because on paper, technically this solution is faster than quick select because it's going to be what? Well, to create this, it takes n time, and then this is going to take k log k time, right? Because you have to find the k largest things in a system and the k smallest. You do that twice, right? So this is basically sorting. It's like a sorting algorithm using a heap, but only for the k largest things. So that's going to be O of n plus k log k time. Now, for space, well, we have to create an additional n plus k space, right? Because we have to create the partition array, which takes n space, and then we have to create this heap that's going to be of size k. So 2k, so n plus k. So technically this is n plus k log k, which is good, but it's slower than quick select, which would be, you know, generally it would take n time to do. But technically on paper, quick select is an n squared algorithm. So this n plus k log k algorithm on paper technically is faster than quick select. But in reality, when you actually do it in practice, it's very unlikely that quick select will result in an n squared occurrence, right? That is very improbable, but could occur. So quick select is faster in reality because the probability that its technical worst case runtime is very low. But if you want to deal with technicalities, this is technically the fastest solution. If you want to deal with reality and what is actually likely to occur, this is a slower solution by a factor of k log k. All right, I just rambled too long, and I'm not a professor or an algorithm professor, so it might have been a little confusing, but hopefully that makes a little bit of sense. So I would just do this in a interview because it's the most intuitive and it shows that you understand heaps and priority queues and greedy approaches. And you might even mention, you know, there's a quick select algorithm. It's technically n time in reality because the likelihood of it hitting its worst case runtime is super improbable. But technically on paper, its worst case runtime is n squared, which is slower than this. That's a summary of that statement. All right, peace out.